I'm going to try and record and get this TV on the camera. I don't think it's going to come out very good, but I'll give it a shot. All right. Oh, wow, I made it. Good. Okay, so I'm going to pass around a few things. First is the quizzes from last time. There's no grades, so nobody can see what you got. The grades I've put online. If you have any questions about your grade, let me know. And then behind the quiz is old quizzes, quiz 1, 2, and 3. If you didn't pick yours up, just go through the stack. Pass that around. Let's start it at this end here. And then the next thing I'm passing out is the review for your exam, which is a week from today, all right? Now, when I put this review together, I had to kind of try and predict what we would finish today. So I don't know if everything on this review will be on the exam. I'll let you know at the end of class, all right? But for now, take one of those. Here you go. There's a couple for everyone here. 2, 3, 4. Is Tuesday?
No, I thought the test was Tuesday.
I think it's Thursday. Well, I'll double check the calendar, but I'm pretty sure it's Thursday. The 28th, I believe.
You got 2 extras.
2 extras. Well, does anyone sit down there normally or no? Only one? Okay. I think there's 4 or 5 here. Let's see. Okay, let's see. That's extras. Any extras? Okay. Just in case. There. Okay, y'all ready? So the exam is scheduled for Thursday. We'll just double check it here. Yep, Thursday. All right. So we will get into, we'll continue on Tuesday with more material, but that material will not be on this exam. All right. We are behind. Today we're supposed to be starting graphing techniques and transformations. We're still in 3.3, so we're going to finish up 3.3. We're going to get into 3.4. So we'll just see how things play out. But Tuesday, no test, right? Thursday will be the test. As far as the review is concerned, you should, of course, do this review, right? I'm not collecting it for a grade. It's just for your own practice. It's to help you kind of narrow down your studying, but don't just focus completely on the review, right? I mean, you still want to, look at the types of problems I'm asking, and then look in your notes, look in your homework, and just kind of like see problems that are similar to those. Look at your quizzes, right? And I pretty much, I won't deviate from this too much, you know what I mean? But I just don't want you to get like tunnel vision on that, that's all. So look at it over the weekend, come with questions on Tuesday. We're not gonna spend Tuesday, Tuesday's a review day, all right? We're gonna keep moving, but I will entertain questions, yes?
When are your office hours again? You said it was before class?
So it varies day to day, but on Tuesday, Thursday, I'm in my office from 7:45 a.m. till right about 8:50. I come over here, And then I have a class after this, and then I'm in my office from 12:30 to 2. And my Monday, Wednesday is similar. The only difference is it's from 1 to 2 instead. I still have the morning ones, but it's 1 to 2, not 12:30. Okay, all right, so today what we're going to do is we're going to continue in 3.3. I'm only going to project up here, and then I'll be working problems out on this board. So last class, what we finished with was talking about where a function is increasing and decreasing and constant. And we finished class with an example of that, and now we're going to get into a new definition. We're going to talk about what's called the local maximum or local minimum of a function. And there's a big old ugly definition here straight out of the ebook. The good news is that you don't need to think about this definition like in terms of all the words. It's a very, very simple visual understanding, all right? So let's say that I graph a function that does this. Okay? That is a function, right? Why is it a function? Remember the test, right? Draw vertical lines, you only hit it one time. Okay, so that is a function. This definition talks about the local maximum. So let me read the definition. A function f has a local maximum at some value c if there is some open interval in, I think that's not showing a little bit of that. Hold on. In I, there we go. In I containing C so that f of c is greater than or equal to f of x for all x in the open interval. What the? Okay, all they're saying is that to be a local maximum, you need to be a point. So this is some c value that we don't know. At this value of c, when I plug that into the function, do you see that this point is higher than the points around it? It's not necessarily the highest point on the entire graph, right? But do you agree that's kind of like the king of the hill, right? That point's like the king of this hill. And so that would be a local maximum. This would be your local maximum. And this point here in red would be a local minimum. Local minimum. And to be a local minimum, it's the same definition except reversed, right? It's instead of being the highest point in that little area, it's the lowest point in that little area, right? So that word local means nearby. Now, local is a weird word, okay, because it's relative, right? When I say that this is the highest point near that point, when I say near, what do I mean, right? Like, are we near SeaWorld right now? Kind of. I mean, it's relative, right? Depends. Like, am I near you right now? Right? So, I mean, it's a relative word. I mean, are we near the sun? Are we near our sun? We're a lot closer to SeaWorld than we are the sun, right? But the sun is very close relative to some other galaxy, right? So I understand it's a weird word, and we're not going to get into the details of that. So we're just going to accept that when we talk about near and close, we kind of get the idea. This point's the highest point near that point. Pretty simple idea? Yes? Yeah? Okay. So let me give you another one. What if we have a graph that does this? Okay. No, local. I'm talking local right now. Okay, so look at that. How about local maximum? Do you see any highest points? Okay, this point right here, right? That's the highest point. Near that point, right? Near that point, that's the highest point. Now, I will say that this is sometimes debated amongst mathematicians, whether or not you include endpoints as local. But in calculus we will, so we're going to do that here. The book doesn't do it because they talk about open intervals, and this is closed on this end because you're including the point. So, but I'm going to put it here. At this value C, right, this right here would be a local maximum. Okay? Are there any other local maximums?
Yeah.
Yes. Right here. See, again, it's not about being the highest point on the entire graph. It's the highest point locally. So that's like a little hill. That's the king of the hill, right? See it? How about local minimum? Do you see any? Two of them. Two of them, right? Here and here. Now, I start to get lazy and I stop writing local, like I already did local max, right? Not local maximum. So here I'm put L min, and here I'm put L min. We good? Now, the arrow that goes up forever implies that that just keeps going up, right? So I don't have a local maximum there because it just keeps getting higher and higher. Okay, pretty straightforward? Yeah? Okay. Now, the next definition, oh, you know what? Let me go back for a second. Let's do that example right there that you can see on the screen. Scroll this up a little bit. There we go. Take a look at that one right there. And what I'd like for you to consider first is local max. Do y'all see any local maximums? So how do I say this, right? How do I say this? I would say for that picture, the local maximum is 2. And it's at x equals 1. So what I'm saying is, look, that's your local maximum, right? That point right there. So what is the local maximum? That's saying what is the y value? How high is that y value? Well, it's 2, right? That's how high it is. Where does it occur? It occurs at x equals 1. Now, if on a test you just gave me the point, you just said 1, 2, I'd be okay with that as well. All right? But technically, the local maximum is the y value. It's the y coordinate, not the x coordinate. All right? How about local minimum? L min. We have a local minimum. What is it? Local minimum is, well, how many do we have? We've got 2 of them. So let's talk about this one first. What's the local minimum value here? The 1, right? So the local minimum is 1, and it happens at what? X is -1, right? So at x is -1, we have a local minimum of 1. There's another one though, right? Right there. So how do we say that? Local minimum is 0, and it happens at x is, can you tell? 3? Do y'all follow that? Yeah? Yes, everyone's good. Yeah? No? Yes? No? Yes? No? Yes? 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 Okay. It's okay to respond to me. All right. Okay, the next definition that we have is absolute maximum and absolute minimum. Now this is talking about the highest point on the entire graph and the lowest point on the entire graph, right? So absolute maximum, absolute minimum. So let's look at this picture right here since I have it on the board. We already identified the local stuff, right? Let's talk about, from that picture, any absolute maximums or minimums. And we'll start with absolute max. So from this picture, do we have an absolute maximum? Is there a highest point on this graph? I'm hearing yes, and he knows. Pardon? Where? This point? Okay, is there any other point on this graph higher than this one? Lots of them, right? Because this goes up, right? An arrow goes up, that implies this goes up forever. And if that goes up forever, is there a highest point? No, right? There's no highest point. So this would have, you just say none, all right? None. You don't have an absolute maximum there. There is no point on this graph that is higher than all other points on the graph. Do you see the difference between a local and absolute? Absolute, you have to look at the entire graph. How about absolute minimum? Yes. Where is it? The second local minimum, this one right here. This right here is also your absolute minimum because it is the lowest point on the graph. No other point on that graph is lower, right? All right, we're going to do some more examples. So let me bring up some more pictures for you. And let's focus our attention on this one here first. There's two graphs here. Let's look at the one on the left first. What I'll do, because I don't know how that's going to come out on camera, I'm going to draw it here. I'm not going to be super accurate with it, but I'll do my best here. So they give us this. Goes like this. Goes up, down, stops here, here, here. Here they give us the 0.01. They give us the 0.36. Give us the 0.44 and the 0.55. All right, let's talk about local max, local min, absolute max, absolute min. All right, local max first. Do y'all see local max anywhere on this? On this? Where are they? Here, this one here, and here. Those are both your local maxes, right? So L max, L max. And so how would I write that? I would say local max of what here? 6, and it's happening at x equals 3. I also have a local max of 5, and it's happening at x equals 5. Okay? All right, let's talk about part. You can just write the point. I just want to be clear that when we talk about local max and local min, absolute max, absolute min, we are talking about the y values. If you give me the point, I understand what you mean. All right? All right, local min. See any local mins there? Here, sorry, keep on pointing over there. These two, right? That one and that one are both local mins. So I have a local min of, what's the local minimum value here? 1, and it happens at x is 0, and then I have a local minimum of 4, and it happens at x is 4. We all good? Absolute max. Is there a highest point on this graph? Yes. So the way I'd say this is I have an absolute max of what? What's my absolute max? Right here. It's 6, right? It's the 6, and it happens at what? X is 3, right? And then I have an absolute minimum. Do I have an absolute minimum? Is there a lowest point? Yeah, right here. That's your absolute minimum. I forgot to put absolute max here. Absolute minimum of, what's my absolute minimum? 1, and it happens at x is 0. Okay. Most students like this. They're like, okay, I get this. This makes sense. I don't have to do any crazy algebra for this. I see it, right? So let's see if we can do something a little more complicated, which is the next example, the one right there in the middle. And I'll draw it again. Any questions? So in Calculus 1, you spend 80% of the semester trying to find the highest and lowest points on graphs. That's what you do. But it's for any graph. It's for any function, can you find the highest and lowest points? And then you realize, or you learn in calculus that we can use that to do a lot of really cool things. All right, so let's see. This picture starts here. Got to be careful here. It comes down, and then there's a hole, and then immediately goes back up like this, and it's a solid dot. This is 1, 2. This is 3, 1, and 5, 3. And the open hole, remember, means that there's no dot there, right? Let's answer these questions again. Make sure I'm recording. I think I'm recording. Yes. Okay, local max. Do you see them? Do we have any? Where are they? Where's that? This one right here, that's a local maximum. Any others? This one right here, right? We have 2 local maximums. Here and here, these are local maxes. They're the highest points in that little neighborhood, in that little area, in that little region. There's no points higher than those. Okay, so I'd say local max of, let's do the one on the left first. Local max of 2, and it happens at x is 1. Then I have another local max of 3, and it happens at x is 5. Okay, is that all right? I might have to start calling on y'all. I always have just same people responding. I might have to do this. Okay, local minimum. Ivan? Where's Ivan? Ivan? No? This will be fun. Wait. Oh, hey. How's it going? How are you? Good? Okay. So you get the hard question here, Ivan. Local minimum. Do you see a point that's lower than all the points next to it? A point that's lower than everything around it. So it makes sense to say 3, 1, right? Because it looks like that's the lowest point. But is this actually part of your graph? Like, no, right? So that's an issue. You can't say right now, you cannot say local minimum, because what would you do? You'd say local minimum of what? 1 at x is 3, but that's not true because that point actually doesn't live on your graph, does it? See, so you can't say that, can you? So this is confusing, yes? So what about the point right next to it? Like there's a point right next to it. Is that the lowest one? Well, then we run into that issue. Remember when I was talking about how, when you're looking at an interval, can you look at the point right next to something? No, right? So if you picked this point, let's just say you picked that point in red and said, yeah, that's my local minimum. I could find one right next to it that's a little bit lower. That would be the one right next to that. And then if I said that's my local minimum, I could find another one right next to that. So this means we have, do we have a local minimum? No. No, we have no local minimum. It's confusing, right, Ivan? But do you understand it? Okay. So none. We would have to have, yeah, that would have to be defined. If I actually fill that in solid, then you could leave this here and we'd be done. Okay?
Not using inequality.
That's if we're looking for domain or if we're looking for where it's increasing or decreasing. Here we're just saying, hey, look, what's the highest y value? What's the lowest, right? So it's a different question. All right. Absolute max. Caitlin. Where's Caitlin? No Caitlin? And Alejandro. Absolute max. What do you think?
The absolute max of 3 at x equals 5.
Absolute max of 3 at x equals 5. Or you could put the point, right? X equals 5. But that is saying what the absolute maximum is. Everyone agree that's the highest point on the curve? Okay, good. Eliana? Okay. Doing all right? Okay. Yeah, absolute minimum. Do you see a lowest point on the entire curve? No, right? There's none. Same thing. There's no lowest point, which is weird because that doesn't, we're not saying that the graph keeps going forever. We're just saying we cannot identify what the lowest point is. We know it's really close to 1, right? It's really close to 1, but how close, right? All right, good. Let's look at let me see if I want to do this one. I don't think I want to do that one. Ooh, that's a good one. That's a real good one right there. The one in the middle. I'll draw it right here. I need to see where that is. It's at 5. There we go. So we have an open circle here at 1, 4. It goes down, comes back up, and then shoots down forever. And it's another open hole here. That sucks. Okay. 2, 2. And then this one is a solid dot, and they tell you it's 4, 3. And this is 5 here, just for reference. That's 0. Okay. Okay, so first thing, everyone understand that dotted line that we see, that vertical dotted line, is what we will later call a vertical asymptote. And the arrow here implies that what happens is this graph goes down and down and down, but never goes past this dotted line. That dotted line extends down forever, and the graph gets closer and closer, never actually crossing over that line.
Wait, would that be a horizontal or a vertical?
Did I say horizontal?
You said vertical.
It's vertical.
Because it's heading horizontal.
No, it's a vertical line though. So the line determines if you say vertical or horizontal.
I had an old teacher that flipped constantly.
Oh, really?
Yeah.
All right. So let's see who's up here. Y'all like this when I call on you? Yeah, you like it? Yes. Okay. Christian, where's Christian? Okay, Christian, you're up. So local max.
There's only one at
There's only one. Okay.
3, and x equals 4.
Local max of 3, and it happens at x equals 4, right? Everyone agree? That's it. That's the local maximum right there. Okay, good. Cranking away here. Desiree, you're up. Excuse me? There's none. Good, there's none. Now this one again, you kind of think maybe that's a local min, but again, it's open, so you can't say it's a local min. And then over here, it just drops forever, doesn't it? So you don't have any lowest point over there. So none. All right. Ian. Where's Ian? Okay. Absolute max? None. Very good. There's no absolute max. There's no highest point on the entire graph. This, again, looks like it could be, but you can't say it's 4, right? You cannot say the highest value is 4, because it never actually gets to 4. What does it get to? Does it get to 3.9? Yes? 3.99? Yes? 3.999? 3.99999, yes, but you can't ever say it gets, like that's the highest, right? So we're just going to say none. And then absolute minimum, none, right? Because again, it drops down forever. Okay. I think you all understand it. Anyone have a question or need clarification?
Why is there no absolute max?
What's the highest point?
Well, it can't be. Well, if it was filled in, it'd be 1.4, but since it's not, wouldn't it be 4.3?
No, but okay, so if you say 4.3, right? If you say 4.3, if you say this is the highest point, what about that point right there? Because remember, all these are points. These are all points, aren't they?
Yeah.
So there are other points on the graph higher than that, so you can't say it's the absolute max.
I didn't see it.
All right, we good? All right, we are moving on. The extreme value theorem. Again, this is a theorem that you will see in college algebra, in calculus. All right, the extreme value theorem. It's actually a pretty simple theorem to understand, but it uses a word that we have not defined in this class explicitly. Like we have not gone into what this word continuous means, like in real detail. So in a class like this, when we say we have a function that is continuous, what that means is you can draw it without picking up your pencil. Okay? If I can draw it without picking up my pencil, that's continuous. That makes sense? I mean, continuous just never stop. You never have to stop and pick up. So this theorem says that if I have a function that when I draw it, I don't pick up my pencil, and it's defined on a closed interval. This is absolutely essential for this theorem. We have to be on a closed interval, which means that we have to start somewhere, A. We have to be defined there, so it cannot be an open circle. And then I have to go to some other point over here, B, and it doesn't matter where it is. As long as I connect these 2 points with a curve that I don't pick my pencil up, and as long as it's a function, right, because it says here it has to be a function, the theorem says if you have that, what's guaranteed? Then, right, so if this is true, then f has an absolute maximum and an absolute minimum. This theorem says you're guaranteed to have a highest point and a lowest point, so long as the curve can be drawn without picking up your pencil, and it is defined everywhere from the left endpoint all the way through to the right endpoint. Okay? Does that seem obvious to you? Yes?
So if there was like a hole in the middle?
If there was a hole in the middle,
Would that be considered picking up your pencil?
that would be considered picking up my pencil. So that would not be continuous. Right? So like in this case, do you all see the absolute max would be here? And the absolute min would be here? Yes? Okay, let me give you another example. What about this?